Hello everyone, I'm Raman Bhati, a PhD student at the University of North Dakota. Today, we are going to examine a few key papers, research gaps, and a proposal for future research directions on automated unit test generation using large language models or LLMs. Specifically, our focus will be on the comparison of unit test coverage percentage, accuracy, and then the usability of automated unit test generation framework for Python language. Let's start with some background and later we will go over some terms I have come across recently. Testing is an essential component of any software development process. There are different types of testing methods available to target different use cases. Among them, unit testing ensures that the code functions correctly, catches bugs early, and then maintains quality. However, manual test creation is time consuming and often neglected. Automating the generation of unit tests is critical for reducing the development cost and ensuring the software quality. With the rise of LLMs, researchers have explored their application in the automated test suite generation. LLM stands for Large Language Model, a type of AI which is designed to understand and generate human like text. LLMs are trained on massive data sets of text and able to predict the next word in a sequence. In the last few years, researchers have tried to explore the usability, code coverage, and accuracy of LLMs in generating new code and unit tests for existing code. The authors from our key survey papers have considered four different families of LLMs in their research studies, and I have listed them here. There are some other terms and abbreviations I have come across while preparing for the survey paper, which I would like to mention here. Codex is a code generating agent from OpenAI, a LLM that can read, understand, and modify the code. Then we have short learning, which is a machine learning framework. And there are two types of short learning we are interested in. The first one is zero shot learning, in which no input sample is labeled, while the few shot learning means some of the input samples are labeled. Finally, prompt engineering is the process of crafting and refining instructions or prompts to guide generative AI models towards producing the desired output. Finally, we have EvoSuite. EvoSuite is a tool that automatically generates unit tests for Java software and is being used in hundreds of open source projects. It is very popular product. Now, moving to motivation, the growing dependence on software applications in our daily lives underscores the vital importance of software testing as a fundamental element of the software development lifecycle. As a result, ensuring that software meets essential performance and security requirements is crucial to maintain user trust and satisfaction. Unit tests aim to directly improve code quality by uncovering defects early in the development cycle and thus significantly reducing the cost and complexity of the bug fixes. They are fundamental for ensuring software correctness, but they are also costly to write and time intensive to design and create. Recent advances in LLMs have shown potential for automating the unit test generation, though existing evaluation often focus on simple scenarios and lack scalability for real-world applications. Clearly, automating this process represents a promising area for research and development. Now, this is a quote I really liked, so I decided to put here. This is from the founder of GitHub, Tom Preston. You are either the one who creates the automation or you are getting automated. With that, let's move to the challenges. all the studies have mentioned lack of generalization as a key challenge. All of the LLM based framework I have seen suffer from their domain specific nature. A test generation tool which is prepared for one use case may not be usable for another. On top of this, the automated test generation tools are language specific. That means a system fully trained to create tests for a whole Java repository may not be able to create a single simple test for Python. Another common challenge I observed is to choose the right dataset for testing their proposed system. For some languages, researchers have created datasets with large number of classes and methods to test. For example, Microsoft has created a huge dataset for Java language called methods to test, which is available in their GitHub repository. I haven't come across any dataset similar to methods to test for the Python language. This forces researchers to pick small datasets which don't reflect the real world scenarios. The next one is hallucination. This is exhibited by LLMs all the time. It is observed that the complex methods and for methods without proper context, the generated tests are simply misleading. They are either incomplete or have mismatched assertions. This is a challenge. However, recent research has shown that by providing enough context with the original method and by providing enough comments or example usage with the original method, this can be addressed up to a certain degree. Last but not least, none of the solutions are complete on their own, meaning users need to help the framework to set proper parameters before initiating the test generation process, or set the version of the language, or set the testing platform version manually. Manual integration of the test results is another pain point of the authors have shared. Moreover, if the LLMs produce incomplete or incorrect tests, the developers would have to go fix the test one by one to ensure that all the tests are working as expected before sending the code to production. Question here is, are the users willing to spend extra time fixing some machine generated tests instead of writing them fresh on their own? So these are the current challenges I have seen so far in the research papers. Now moving to survey questions, methods, source and classification. The first question I have is about the usability of LLM based networks frameworks. I did not find many papers which cover usability at length. The second question is about the quality of tests the framework generates and what metrics have they used to measure the quality of the tests. Almost every single paper I read had discussed this point in one way or another. The third question is about the effectiveness of test suites for detecting bugs. If there are bugs present in the current code, how does the test suite detect it and reports it? The fourth one inquires the influence of prompt engineering in the correctness and the compatibility of generated tests. Finally, we have add if we add an explanatory comment to the code under test, does it make any difference to the metrics? And then the last is about is there any study on comparison between the performance of LLM based suites and any existing frameworks like EOSuite? If there are any comparisons exist, then the survey question 6 focus on that. Next is the paper selection criteria. The first selection criteria I had was the relevance to my chosen research topic. If the topic is not relevant, then I would simply discard that. So I started the search for papers with the keywords LLMs and unit testing or AI and automated unit testing, and I was able to find many good research papers from the recent years which were also my second selection criteria. Finally, I wanted to choose at least one or two good papers from other languages like Java and JavaScript so that I could compare them with the Python papers and see the challenges on the both sides. That was my last selection criteria. For literature sources, these are the sources of the papers I found. All of the papers I was able to download from UND's digital library. Now moving to the survey method. To find the right papers, I searched these keywords like automated unit testing or AI for generating unit tests and so on. Once I had enough papers to work with, I filtered those papers by their publication dates, including the ones published in the last 2 or 3 years and discarding the rest. This was done because of the ever changing behaviors of LLMs, and then the newer versions of LLMs offer so much more and different than their previous counterparts. In this phase, the rest of the filtering was done after reviewing the abstracts and the conclusion of the candidate papers. Once the filtering was done, I grouped them by languages and then by specific LLM platform where the study was performed. This helped me to compare their test results since many of the parameters were common. I looked for common metrics in those papers and then compared the results. Finally, evaluated the papers based on my survey questions. The next one is classification and the comparison of the key papers I selected. So in this slide, I present the comparison of the key survey papers on 5 dimensions. The first column shows when the paper was published and which language the study is focused on. The second column compares the papers on their input sizes while performing their research. As we can see, the paper number 2 used the largest dataset of around 150k Java classes to perform their study. This study is closest to the real world scenario. The third column evaluates the papers based on their comparison choices and which system they chose as a benchmark to test their own system. As we can see, EvoSuite seems to be a popular choice against comparing their own system because it's an already established framework. The fourth column shows various LLMs used by the authors to perform their studies. And then finally, fifth is one of the most interesting as it shows popular choices for evaluation metrics. As we can see, around 80% of the studies choose prompt engineering as a significant parameter to test their system. Also, as expected, 100% of the authors chose test coverage percentage as one of the metrics. Only one paper discusses the usability of LLMs in depth. Now, in the key survey papers, I considered these 6 dimensions, and based on that, I find the research gaps and future directions. As it is evident from the previous slides that most of the papers lack a comprehensive study of usability of LLMs in automated test case generation frameworks, it would be useful to have one research study dedicated to measure the user's efforts and their satisfaction while they use LLMs to generate the test cases by setting various input parameters. Also, it might be useful to measure the amount of time they spend in order to perform the whole task end to end. It would be good to have more studies use larger data sets so that their proposed system can be tested against real world scenarios. As we observed that in some of the studies, users had to perform the manual integration tasks to generate the test reports. A dedicated study on this topic might shed some more light on how automatic integration with the rest of the CI/CD pipeline can increase user satisfaction and improve usability of that system. Similarly, no single study provides a comprehensive view of all the evaluation metrics we saw earlier. One dedicated study on scalability of the framework is needed, which focuses on framework's performance against its input size. For example, it might be useful to measure the KPIs for 100 Java classes and then increasing it to 1000 Java classes with or without context, and then scale it to 100k Java classes and so on. We also need a large data set for Python language, something similar to method to test project which is available for Java. This slide compares the key papers based on 5 dimensions. The first column shows how many studies have considered usability, and based on the entries, it seems that only 2 of them have considered exploring the usability and only one discusses it in depth. The second column shows the consideration on the integration part, and it looks like 75% of the studies have addressed the integration problem in one way or another, and some of them have actually integrated their framework with tools like Spotbug, Jacoco, and Checkstyle, which are very popular tools among the developers who code in Java and Spring Boot. The third column is about input source and size, and as we can see, these studies vary drastically on the input size. I could not find any research paper on Python which take huge data sets as input sources. The fourth column discusses the actual output of the framework and then the classes of observation. A framework might generate tests with syntax errors, tests with incorrect parameters, with unresolved references, lookup errors, etc. Only 50% of these studies show that their framework struggles with these practical errors. The rest of them are silent about it. Now, this is important because all of the LLMs show or exhibit some kind of hallucination. So not having these issues is little bit difficult to believe. The last column we have discussed in depth earlier, which is related to usability study, and we are not going to go over it again. Moving to research direction. Finally, we discuss future research directions based on our evaluation of these papers. As expected, the first one is usability study specifically designed for Python language. We have already discussed this at length in other sections. This direction is actually tied with another human in the loop direction, since we would want to identify how feasible it would be to replace manual unit test generation with automated frameworks. One extremely important research direction is to increase the reliability of LLM's output, since LLMs exhibit hallucinations. So one dedicated study to identify on which input parameters the LLMs hallucinate, and its solution is needed to address the research gaps. Another area is to examine the automated integration feasibility. The integration of the test generation framework with test reporting tools and with CI/CD pipeline to have the system production ready. Last but not least, I certainly feel the need of having a standard larger dataset for Python, something similar to methods to test. The next slide here is for citations. Here I have included all the research papers from which I took any material, and also some of those papers which were frequently cited in our 4 key papers. With that, I finish my presentation part. Thank you so much.